Today we're going to continue our discussion about continuity. We're also going to discuss a well-known theorem that you did touch on in pre-calc called the intermediate value theorem. Keep in mind as we learn theorems, any theorems that have a name you should especially know. Other theorems that don't have names you should at the very least understand. You don't need to know, oh, that was limit theorem 6. Just know, especially know the ones that have names and what they refer to. So, let's begin. Theorem 6 just gives you a couple of rules, and those rules are that the limit as theta approaches 0 of cosine is 1, and the limit as theta approaches 0 of sine is 0, and that you should know because you know what sine and cosine graphs look like. Since tangent is sine over cosine, it is continuous everywhere except for cosine. Therefore, tangent of x has discontinuities. Where does tangent have discontinuities? It is when cosine of x equals 0, which is pi over 2, 3 pi over 2, 5 pi over 2, and so on. Easier way to write that might be pi over 2 plus pi n. The following types of functions are continuous at every number in their domain, which means we need to find their domains. Pause the video, take a second, and fill out their domains. Now that you've answered all of these domains, you will know that first one, polynomials, we talked about it yesterday, are all real numbers, and that was from definition theorem 5 that we talked about yesterday, theorem 5. Now this one, negative infinity, the terrible infinity, negative infinity to negative 1, negative 1 to 1, and 1 to infinity, because the denominator can't equal 0, and that happens at 1 and 0. H of x is a little bit different. It's going to be from 0 to 1 and from 1 to infinity, because in a radical has to be greater than or equal to 0, but the denominator can't equal 0, so everything 0 and bigger works except for 1. Now, some of these trig ones you should know just based on your knowledge of the graph. Sine doesn't have any jumps or holes or asymptotes, so it's negative infinity to infinity. Same idea for cosine, and tangent refers to what we talked about earlier. It's going to be all real numbers except x equals pi over 2 plus pi n, which would give us every asymptote at pi over 2 and 3 pi over 2 and 5 pi over 2 and negative pi over 2, etc. Theorem 8 says if f is continuous at b, and the limit as x approaches a of g of b equals b, then the limit of f of g of x as x approaches a equals f of b. In other words, the limit of f of g of x is equal to f of the limit of g of x. So, I'll give you an example. If we do the limit of f of g of x and the limit it could also be written as f of the limit as x approaches a of g of x and the cube root of the limit as x approaches a of g of x. So the limit symbol can be moved as long as on the outside the function is continuous at the a value we're finding the limit at. Theorem 9, if g is continuous at a and f is continuous at g of a, then the composite function f of g given by f of g of x or f of g of x, two different ways to write it, is continuous at A. So that's a little bit of common sense. If they're both continuous, then their composites are also continuous. Theorem 10, the intermediate value theorem, says suppose that f is continuous on the closed interval. Continuous meaning no jumps, holes, asymptotes. Another way to think about it is that you can draw the function without lifting your pencil. And let n be any number between f of A and f of B. Then there exists a number c in A and B such that f of c equals n. For instance, if we have a function, let's say we know this function goes through to 1, and we know it goes through 5, 5. And it's continuous. That means somewhere between 2, the y value of 2 and the y value of 5, it has to equal 3 at some point, no matter how I draw it. So it could look like a straight line, it could look like a polynomial, it could look like lots of things, but no matter how you draw it without lifting your pencil, it has to cross this 3 value in the middle. So, our examples here say, show that the function has a root in the specified interval. If you have a function and you want to know if it has a root, it's a continuous function. That means some point's going to have to be below the x-axis and some point's going to have to be above. If it's continuous, it means they're connected, can be drawn without lifting your pencil, then it has to cross that x-axis somewhere. So, all we do is take f of 1 and f of 2 and hope that one is positive and one is negative. Now, if we plug in 1, we get negative 1. If we plug in 2, we get 12. Based on that, therefore, that's what those 3 little dots mean, therefore, f of c equals 0 between 1 and 2. Similar idea here. Move it to one side, and we're going to find out. It's a little bit different though. Notice how this one had brackets and this one has parentheses. That means the beginning point and the end point are not included. And you'll see that if we take f of 0 and f of 1.4, we get f of 0 is f of 0 is 0, and f of 1.4 is 1.002. That doesn't have a sign change. It doesn't definitely cross the x-axis. Does it touch it? Maybe, but it doesn't necessarily cross. What this means is that it crosses somewhere between there, so maybe we need to move in a little bit. If I'm 10 feet away from you and someone's between us, if I move closer to you, that person could still be between us. So let's try something like f of 0.1. I want to move so far that I miss the 0, but I want to move far enough that I'm not at 0 anymore. So once in a while, we need to hunt around. Now, f of 0.1 is negative. F of 1.4 is not negative. Therefore, f of c equals 0 is 0 to 1.4. If you have questions on that, come ask me about it in class tomorrow. We'll have an opportunity for questions tomorrow. Finally, for what value of the constant c is the function f continuous? Well, to be continuous, the limit equals the value. If we talk about this, cx plus 1 is a line. Its domain is all real numbers. Cx squared minus 3 is a quadratic, a parabola. Its domain is all real numbers. So we don't have any issues with either function. The issue arises at the 2, when it changes from one piece of the piecewise function to another piece of the piecewise function. We need to know if those touch, because if they touch, then the limit's going to equal the value. But if they don't, then there's a jump, or there's a hole, or something like that. So we need to know cx plus 1 is equal to cx squared minus 3 at 2, which means we have to plug our 2 in. We get 2c plus 1 equals 4c minus 3. 4 equals 2c. We move things around a little bit. So c equals 2, which means c equals 2 is the value that would make this piecewise function continuous everywhere. Each half is already continuous. The only question is at the point when it changes from one function to another. Come with questions tomorrow.